Inner coupling and ultimate unification of gradient and mirror descent. This is a joint work with Lorenzo Arrecchia, who is now at Boston University. So first, apologize for my voice. I caught a cold before I come here, so try to stay a bit away from me. In any case, in this part, let's focus on, say, the simple problem of minimizing function fx. So for simplicity, let's assume that the function is differential, convex, and say we're working in some n-dimensional Euclidean space. Okay? Then if I draw the convex function here at every point x, I can compute the gradient of the function, which is a linear lower bounding hyperplane to the convex function, and it also tells us roughly where we should look for the minimizer of the function. In particular, if I denote by x star the minimizer of the function, then the goal of the so-called first order method is to try to minimize the number of Curry points x1 through xt, so that in the very end I can find an approximate minimizer whose objective distance from fx to fx star is at most epsilon. Okay, so say this is the goal of today's talk. We want to find an epsilon approximate minimizer of a convex and differential function. So if you look into literatures, there are tons of first order methods. And one of our first kind of section of the papers is to actually, we did the literature review, and we categorized essentially all existing first order methods into two categories. One of them we call gradient descent. That is something very simple. For any method whose goal is to decrease the objective value at each iteration, then we call it gradient descent. Okay? So say the function maybe at x1, he sees the gradient, then he can roughly know where to go to decrease the objective value. So whenever a method behaves like this, we call it gradient descent. And this is in contrast to a different class of functions that we summarize as mirror descent. That is something from the dual side, from the lower bounding side. So without giving you any math, let me just use pictures. So at any point x, remember the gradient actually also gives us a linear lower bounding hyperplanes. Okay? At a different point, so then the whole point, the entire goal of mirror descent is to intelligently select those points to Curry so that the final average of those hyperplanes, which is another linear lower bounding hyperplane, right? Then the goal of mirror descent is to try to make this final hyperplane as flat as possible. Then you can actually quantify this. Then the flatter it is, the faster mirror descent converges. So from the pictures, already we can make two very important observations. For mirror descent, if we keep receiving gradients that are flat, meaning that are small, the norm are small, then it converges faster because it's easier for us to get a flat red hyperplane. To the contrary, if we keep getting something very steep, very large gradients, then it converges slower. If you ask me to use one sentence to summarize mirror descent, here is it. Small gradient implies faster convergence, to summarize mirror descent. So this is in contrast to gradient descent, in which the larger the gradient we should receive, then the more we can decrease the objective value. The smaller it is, then the smaller we can decrease. So large gradient implies faster convergence for gradient descent. Now if you stare at the properties of the two types of method, the natural question arises, which is can we combine the analysis of the two to get an even faster algorithm than any one of them alone? The answer is yes, but with some difficulty. So intuitively, at any point x, say xk, at iteration k, then if we see that the gradient is large, we want to do gradient descent because gradient descent performs better. If the gradient is small, we want to do mirror descent. So at this step, we're very happy, things are very simple, but from the next step on, we're in some trouble. So if we keep getting, for instance, large gradients, we can keep decreasing objective one by one, and we're very happy. But unfortunately, the gradients we are receiving may be alternatively large and small. And if this happens, we're in the scenario like this or the other one, we're in some trouble. Because, for instance, gradient descent must be executed in a consecutive fashion. Meaning that, remember, gradient descent tries to decrease the objective, but if we alternatively do like gradient and mirror descent, we may not necessarily decrease the objective very much. We may zigzag, and sometimes it doesn't even converge. So if I use a 2x2 matrix to summarize this scenario here, it basically says if I get the same types of gradient, say between two consecutive iterations, then we're happy. Otherwise, we're not. One can actually quantify this. I'm skipping the details. So by looking at the 2x2 matrix, we definitely know what's the best answer. That's to play a mixed strategy. So what we should actually do, proposed by our paper, is to choose a linear combination of the two strategies, a linear combination of gradient and mirror descent. Here the combination ratio, tau, is between 0 and 1, is to be tuned. It depends on the problem, so I'm not going into the details. But that's like the rough idea of linear coupling. And in particular, it gives rise to the so-called 1/√epsilon convergence rate, meaning the number of iterations is inversely proportional to square root the accuracy. This is known as the accelerated convergence rate, which is, by the way, quadratically faster than any of the two methods alone. So by combining two things, you not only get twice faster, you get quadratically faster. So this is one contribution of the paper. That is, we showed that this framework of linear coupling gives rise to accelerated convergence rate. So this contribution itself is not necessarily the most significant because Nesterov already proved something similar using a different proof 30 years ago. So what I find really amazing about this linear coupling framework is that it's actually not a single method, but it's a way of thinking. Whenever you face a new problem, it tells you how you should design optimization-based methods, as we will see on the next slide. In particular, it does apply to many other problems, like the original Nestrov's proof does not, most of them, it does not apply to. So let's see why on the next slide, from a very high level. So linear coupling, if I summarize it just in 3 lines, it has a gradient descent lemma, it has a mirror descent lemma, and a convexity lemma. So you don't need to read the math, but basically the larger the gradient is, then gradient descent performs better. It's on the other side of the inequality. The smaller the gradient is, then the mirror descent performs better. And then finally, if I choose a linear combination of the two methods, I use convexity to argue about the properties of the 3 different points. Then if you write down the inequalities, you just sum them up using essentially the only possible ways of parameters. Then you get what I claimed on the previous slide, the 1/√epsilon convergence. But what is more amazing here is that those are only generic lemmas. They apply to essentially any smooth function and period. But for a specific, say, theoretical computer science problem or whatever problem you have in hand, then you'd better design maybe your own gradient descent lemma, your own mirror descent lemma. So we even, for instance, have a paper to tell you like how to design the best possible mirror descent, like for a specific problem, which I'm not going into the details. Now the beautiful part about linear coupling is that whenever you do so, you design a gradient descent or mirror descent, the same ideology, the same idea of combining the two methods still works. You can still use linear coupling to combine them, and very likely you're going to break some state of the art and get an even faster running time. So the amazing things actually even continue. So last year, we even realized that we can get rid of convexity. So if we enforce the 3 points to be the same, and somehow get rid of the third line, then the previous 2 lemmas still work, and you can still combine them. And that is what we call weak linear coupling, and you can actually generalize the idea to also apply them to non-convex optimization in terms of getting a local minima, definitely not global. And even more, like this is about 2 sequences of points, but if I do a 3rd sequence of points, whatever that means, for some problems it could be beneficial, and then I can choose a linear combination of the 3 to get even faster running time. We call this like 3-way linear coupling, and that is actually why there are many applications here. So for different types of problems, you apply maybe 3-way coupling or weak linear coupling. And those results also have their, say, TCS and the machine learning applications. So thank you.
Questions?
Hey, sorry, I was confused on the slide where you introduced weak linear coupling. So how do you force YK and ZK to be the same?
So basically on this Oh, yeah, sorry, on that slide. So typically, like there's the gradient descent and mirror descent, and then 2 points you do the linear combination. But sometimes you can use the same sequence of points, x1, x2, x3, but applying 2 different analyses, gradient descent and mirror descent, simultaneously on the same sequence of things. So one giving an upper bounding like lemma, the other one giving a lower bounding lemma, and somehow surprisingly this breaks, what people typically get, and it gives faster running time. So I can show you some papers on that.